Good evening, all of you. Today, this evening, we are here. We are organizing one webinar on the industry prospect in quantum computing. Our resource person is Mr. Amit Saha. At first, I would like to invite all of you, and I will request our HOD, Dr. Dharampal Singh, to say a few words about this, about the webinar and our department. Yes,
Thank
sir.
you, Sonali. At first, I would like to welcome all the participants, those who have joined here, because I can see here our maximum faculty and lab staff are there, and those who have joined through the YouTube link. So today's topic is the quantum computing part. So quantum computing is known as the future computing there, and I'm thankful to our today expert, so our Amit sir. So on behalf of the CSE department, JS College of Engineering, I would like to welcome him first, because without the expert, webinar is not possible there. Also, I would like to thanks to our Madam Sonali Madam, because the short period of time she has contacted the consultant and the scientist, those who are doing the research on quantum computing. So topic is a very new one, and this topic is known as the future of computing. So I hope that those who have joined through the YouTube live, they can get the idea about it, and they can implement this type of things in their research work. So I hope that this program will be the successful one. So best of luck for the program from my side, and I will also request to our expert to start the session, because our participants are eager for your lecture, and I hope that they will learn the thing and implement the idea in their research work. Madam, I will not take the much time there, because already we are late for the 15 minutes. Yes, so, sir. Madam, over to you.
Okay, thank you, sir. Now I will, before starting the program, before going to the session directly, I will introduce our honorable speaker today, Mr. Amit Saha. He is currently working as quantum expert, and he is a consultant at the Atos. So he was a senior research fellow from CSIR from 2017 to 2019. His current research interests include quantum computing, quantum algorithm, quantum circuit synthesis, etc., and multi-valued quantum computing, quantum image processing. And he is the author of many papers and on this topic. Okay, so welcome you, sir. Welcome you, Sir Amit, sir. Now the stage is yours. You can start, sir.
Yeah. Thank you, Sonali ma'am and HOD sir for introducing me in a nice way, and thank you for inviting me and giving me the opportunity to present myself about quantum computing, which is a hot topic right now in the all over the world. So let me share my screen first.
Sir, I think I am the host. Yes, sir, it is visible.
Is it okay?
Perfectly.
So, so it is already mentioned that today I'm going to talk about quantum computing and its industry prospects. And myself, Amit Saha, and I'm currently working as a consultant.
Recording in progress.
And quantum expert at Atos. So those who don't know about the organization Atos, Atos is an IT giant based in Europe, especially in France. So it has almost 110,000 employees, more than 10,000 employees, and among all the employees, we are probably 30 or 35 odd pupils who are working on quantum computing. And as you see that as per my today's topic, there are two parts in my presentation. First one is all about quantum computing, the overview of it, and the second part will be the industry prospects in quantum computing. So let's start with the quantum computing part. So uh, so my first slide is all about quantum computing is a myth. So back in 2015-16, when I finished my master's, I was preparing to start my PhD in the domain of quantum computing. Several people were not very much sure about the quantum computing. Many people were believed that quantum computing is just a myth, and it's a completely theoretical, and it's completely theoretical, and the mathematical, it's not going to be experimental very soon. It's a complete rocket science, and maybe after 100 years it's going to be live. But this myth has been broken, I must say. Quantum computing is not a myth at all. It's now well established domain among the researchers, among the industrialists, among the students, for its quantum advantages compared to its classical computers. So after breaking the myth that quantum computing can be experimentally proved, a new myth has come to our end, and that is the biggest myth right now, that quantum computing can solve any problem in the world with blink of an eye. So it's a big no, because quantum computing is not going to solve all the problems that we have. It cannot solve all the problems with blink of an eye. It cannot be possible. There are some limitations which quantum computing has. So what actually quantum computing is then? So it's not a myth, it's proven. So it is becoming very popular, and it's not going to be it is not going to solve all the problems with exponential speed up, or I can say very fast. You can take quantum computing as a promise. Okay, so quantum computing is a promise that it will solve some computational problems, some complex computational problems, faster than the current supercomputers or the classical computers. So it will take some complex computational problems, and it will solve in much faster time. That those problems cannot be solved in today's world because of lack of resources. So if I summarize my last three slides that I have presented over here. So a timeline can be portrayed here. So let me start with 1981, when first time Professor Richard Feynman, a famous scientist, proposed a concept of quantum computer. So she proposed a very basic model of a quantum computer. From that point, the whole world was started in doing something about quantum computing. So after that, from the same institute, MIT, Professor Peter Shor, came up with his famous idea that is known as Shor's algorithm. That is a quantum algorithm which can factorize the large number in polynomial time. So in 1994, that was the first time someone proposed and analytically simulated, analytically not simulated, analytically designed a quantum algorithm for the first time. So from there, a new era has been begun. So after 2 years, in 1996, Professor L. Grover came up with his masterpiece idea that is known as Grover's algorithm, which searches the unstructured database in quadratic speedup. So I'll cover this algorithm in later part. So just for the beginning, how quantum computing evolves in today's world. So I just want to portray that thing. So this is the phase where it was more like quantum computing is a myth. So it is completely theoretical. Shor's developed an algorithm, Grover developed an algorithm, but it cannot be experimentally experimentally exhibited. So that is the main challenge. So I just want to share my experience here. So when back in 2015 I was starting my PhD or planning to do a PhD. So that time I was very confused because the future of what would be the future of quantum computing. So that time it was in 2015. 2015 or early of 2016, it was a complete myth. So in the last month of 2016, it was historical. IBM introduced a quantum computer with 5 qubits. I'll talk about qubits later in my presentation, but IBM came up with a quantum computer that just shook the world. All right. So so everyone now started to believe that yes, we can experiment quantum computer. So as I am representing my organization Atos was not far behind from the other companies. Atos introduced its first quantum learning machine, that is the most powerful quantum simulator in the world in 2017. So from that era, we started believe that quantum computing is no longer a myth, but we started to believe that yeah, quantum computing is going to change the world. Quantum computing is going to solve any problem in the world with blink of an eye. But it's not true, because currently we are facing several problems with the current quantum computers. I'll talk about this, and this era is known as NISQ. NISQ is nothing but okay. Can you show my mouse pointer? Can you visible it?
Yes, sir. Yes.
Okay. Thank you.
Yes,
Thank you.
visible.
Yeah. So NISQ all about noisy intermediate scale quantum computer that is currently present in today's world. So don't worry about this term, but today's quantum computer is known as NISQ. And we believe that it is not going to be scalable in down the line 5 to 10 years. It's not going to be a huge quantum computer. It might be small computer for the experiments that the researchers are doing right now. And after 10 to 12 or 15 years, it will be more scalable. Then we can believe that yeah, larger complex problem can be solved in much faster time, but not today. We can do that. So this is the overall timeline and the myths about quantum computer that I have tried to present here. So as Shonali ma'am told me that we are from computer science background. All the participants are likely to be computer science background. I am also from computer science background. So we all talk about the complex computational problems with respect to complexity classes. So we all know these classes very well, that there are some computational problems which belong to a P class. P stands for polynomial time solvable problem. And there is another class that is NP, that is non-polynomial, non-deterministic polynomial time solvable problem. And we know that which are the most hard problems belong to the NP classes are known as NP complete problems. So you can see that here is another complexity class, that is BQP. What is BQP? So BQP is nothing but bounded error quantum polynomial time solvable problem. All right. So bounded error quantum polynomial. So from BQP we can exhibit that these are the problems we are going to target to solve using a quantum computer. So we are not going to targeting the NP complete problem, because it's just giving quadratic speed up right now. So I'll talk about more in details, but you can see that some NP problems has been addressed using quantum computer. So one of the problem is Shor's algorithm. Shor's algorithm is based on factorization problem, and factorization problem, we all know that it's a NP intermediate problem. What is NP intermediate? It's not in NP complete, it's not in P, it's all about NP. So it is NP intermediate. So we can see that this area this area belongs to NP classes. So we can see that quantum computer can solve these problems with much faster time that today's classical computer cannot do. In fact, today's supercomputer cannot do. So more elaborately, we can describe this computational complexity part. So from BIGO notation, we know that when the problem size versus time is 2 to the power n, we call it exponential. And this is all about the NP problems and NP complete problems. And the P part and the polynomial part is nothing but n square or n or log n. So our main goal is here to reduce any 2 to the power n problem, exponential problem, into the polynomial classes. So already in 1994, I have already told that Shor has came up with so Shor has come up with his brilliant idea, that is factorization problem. So he showed that in classical computer it takes it takes 2 to the power n times to factorize a large prime number, and for a quantum computer it will take only n. So you can imagine that. So let me give an example. Based on factorization, today whole world's crypto system is based on. So what does it mean? It means that whenever you are giving some password in some server or in some websites, like when you are accessing your mobile banking or the net banking, you are giving some password. So it's completely based on the RSA crypto system, and RSA crypto system is based on the prime factorization. So you can imagine that if quantum computers will come in 3 to 5 years, in next 3 to 5 years, it will break all the RSA crypto system. Then our mobile banking or net banking or Facebook or any where we use passwords, it can be breakable with quantum computers. So it's really alarming. We have to think about it more, because if a quantum computer comes for 3 to 5 years, everything will be breakable. So this much fascinating quantum computer or quantum computing is. So you can imagine it. So I mean, why quantum computing is different from classical computer? What are the ingredients it has to become so powerful, isn't it? So let me put it in this way. Like as we all work with classical bits in computer science. It's all about classical bits, 0 and 1. Every computer only understands 0 and 1, and those are our classical bits. Similarly, quantum computer or quantum computing has its own bits, that is qubits. So qubits is it's similar to classical bit, but it carries only the quantum information of it. And and just see this sentence, because I'll prove this sentence in future, that n qubits can have 2 to the power n number of information. Okay, so as we know that classical bits can hold only 0 or 1, that means one classical bit can only hold one information. So n number of classical bits will be holding n number of informations, but n number of qubits can hold 2 to the power n information, and that is the biggest advantage, I can say, biggest advantage from the quantum computing paradigm. So next quantum mechanical property is state superposition, or the qubit superposition. So you can see here one simple example, that if suppose if you are tossing a coin. So when you are tossing a coin and it is in the air, you don't know what will be the outcome. It could be 0 or it could be 1. So when it is in the air, so it is actually in either it is actually in 0 and 1, or I can say it is actually head or tail state. I don't know which is going to come into my hand. So quantum computing is actually similar to this coin tossing. Qubits are like, it can hold 0 and 1 at a time, like a coin in the air is having a 0 and 1 at a time. And similarly, when I observe that coin, when I hold that coin into my hand, then only I get the information that it is either head or it is either tail. So quantum bits are nothing else from a coin. Whenever we observe that quantum bit by the measurement operator, then only we can have the 0 state or the 1 state with some probability. If I tell you that please coin a toss and before measuring it, tell me what would be the outcome. So you will going to tell me that it's half probability of 0, half probability of head, and half probability of tail. So it is similar, like for a qubit, when you measure it could be half probability of 0 and it is half probability of 1. That's why quantum computing is so powerful, because classical computer can hold so classical bits can hold only 0 or only 1 at a time, but the quantum bits or the qubits can hold hold the combination of 0 and 1 with some probability. So next thing is quantum entanglement. Don't push yourself much. I'm just giving you the definition of quantum entanglement here, and I'll talk about more in the later part. So as we know that as we understood that that qubits can be superposed. That means n qubits can have 2 to the power n number of informations, whereas n classical qubits can have n number of informations. So but whenever we are measuring it, we actually evolve to a classical information. What does it mean? Like whenever you have a superposed qubit, it could be 0, it could be 1, but when you are measuring it, it either 0 or 1. So it becomes classical again. So quantum entanglement is a very beautiful property that quantum mechanical has. So it is actually it can be defined as qubits can have correlations. What does it mean? It can interact. Two qubits can be interact, uh, maybe in the speed of light. So if a qubit, if I measure a qubit, then if it comes 0, and the entangled qubit with that 0 will come also 0 if they are having the same properties. So it becomes very beautiful that these qubits, if they are far from different universe, they are also connected by some correlation, and if we measure one qubit, then the other qubit, we will have the other qubits output as well. So I'll show the entanglement more technically in later part of my presentation, but I just let you want to know that that these are the fundamental properties that quantum computing has, and for these properties quantum computing is gaining from the classical point of view. So let's take an example, a simple example, to understand what is actually happening into quantum paradigm. So I have taken four cards here. Okay, so from these four cards, one is a hearts of king, and I have to search through the computers which one is the heart of king. So in classical computer, what we'll do, we have these four cards, so we don't know which one is heart of king. Uh, so at time 0, all are unknown to me, but at time 1 I'll start the so it's completely, it's like a linear search in computer science, isn't it? So it's an array of information, and we have 4 information. At time 1 we'll check the first card, and it comes that it's a king of spade. At time 2 we'll check, and it comes that it's a diamond of it's a king of diamond. At time 3 it's a king of clubs, and at last we'll see that we found that it's a king of hearts. So can you please tell me that that how many resources are used here and how much time it takes? So I thought it will be more interactive session, but yes, I'm just going to tell you that we have used only one computer here. So resource is 1, and time has taken 4 unit. It may be seconds, it may be microseconds. So 4 unit time has taken our classical computer that we use, that we always keep in our pocket. So it takes so it is only one resource, and it takes 4 unit of time. So for parallel computer at time 0, it is remains same, like it has all the cards are unknown. At time 1, we can see all the cards if we can parallelly check all the 4 cards at a single time. What does it mean? That means we are using 4 different computers or 4 different chips or 4 different resources, whatever you understand, you can think of it. All right, so you are using 4 different resources at a single time, and you can have the king of hearts in a single unit time, but you need 4 resources here. So in classical computer that we are using as mobile or computer, it is 1 resource, 4 unit time. For parallel computer, there are 4 resources, but time is much less than the classical computer. So what is happening with quantum computer? So I just I think I have written this quantum computer 2 times. I'll eradicate that one computer later. All right, so at time 0, we also like previous 2 examples, we have the 4 unknown cards. At time 1, we can see all the cards if we are simulating this problem in a quantum computer. So resource is 1, but time is 2 unit. But how? I mean, why 2 unit? It must be 1 unit, isn't it? Okay, let's see in the next slide. So I promise that Sonali ma'am has told me that there are BTech or MTech students, most of the BTech and MTech students, and I try to keep my slides so simple that anyone can understand quantum computing from my today's presentation. If anyone from school level, he or she can also understand what I'm going to tell about quantum computer. But this is the one slide where I use some notation, some mathematical analytics. All right, so don't bother about it. I'll explain everything. So this one is the Kate notation. Just for better understanding, this is known as the Psi state. So this is the quantum state we are developing here from this problem. So in quantum state, we can have the superposition of this four information, and I have done the same thing in this equation. So this is a quantum state, and king of spade, king of diamonds, king of clubs, king of hearts are in the superposition with the amplitude. Just remember the term amplitude. Amplitude means when you are square, if you do the square of the amplitude, you will get the probability of getting that information. That means if amplitude is 1 by root over of 4, that means the for getting king of spades, the probability of the quantum state is 1 by 4. For getting the king of diamonds, it's 1 by 4. Similarly, for others, it's 1 by 4. That means it is equally superposed. That I have already told. We can do that by the superposition. So at time 1, it's nothing but a superposed states or the quantum states of these 4 cards with the amplitude of 1 over root 4. Forget about the amplitude, just remember it's like 1 by 4 probability. Okay, so at time 1, all the cards with 1 by 4 probability. So if now suppose I measure the quantum state, as I told previously, that we have to measure measure the quantum state to observe the final outcome, because we are searching king of hearts. So we have to somehow measure the quantum state. So if we measure at time 1, so it will give me a random number with equal probability. That means we cannot have the desired result. We are searching for king of hearts. We are not searching for king of spades or diamonds or clubs. But at time t1, quantum computer will give me equal superposition of all the information, but that is not required to me. So what is a requirement here? We need a king of hearts with 1 probability and others with 0 probability. And how it will be done? It will be done using Grover's algorithm that I mentioned. L. Grover proposed in 1996, that unstructured database searching problem. So Grover's told us that you have to iterate at least root over of 4 times, that is nothing but 2 times, for these specific problems. If you iterate, or if you run this quantum problem as a search problem for 2 times, you will have the king of hearts with 1 probability. That means you have a resource 1, that is the quantum computer, and time taken is 2 unit. So so in classical computer, resource was 1, but time was 4 unit. In parallel computing, resources are much higher, so cost should be in higher part. Resources are 4, time is 1 unit, yes, a lot faster. And in case of quantum computing, resource is one quantum computer we need, and time is 2 unit, because we need to iterate 2 times this such problem, as this search algorithm, this search algorithm. That's why it requires 2 unit. So you can see that here is an example of how this king of spades or king of diamonds, this information can be fetched into quantum computer. These are nothing but the qubits. So you can see that if there are 4 information, we can have the 4 number of quantum basis states, and it can be so for to represent 4 information, we need 2 number of qubits, isn't it? So using 2 qubits, we can have 0 0 0 1 1 0 1 1. So we have to so if there are 4 information, we have to do the logarithm of it to calculate the number of the qubits. So you can see that only 2 qubits quantum computer machine can search this king of hearts in 2 unit of time. But have you imagined why we are going to search this king of hearts in a complex manner, like what I have done with the quantum computer? Just imagine if we have 2 to the n number of such space. That means, like, here we have 4 number of cards. Just imagine we have 2 to the power n number of cards, and the n is very large, like the value of n is 100. Then it will become tough, because 2 to the power 100 is like a, I mean, is more than the age of our universe. So if you want to search king of hearts from 2 to the power 100 informations, it will take 2 to the power 100 unit of times. That is maybe billion or trillion of years. it will take getting difficult. So what about, so I'm recently talking about the classical computer. It will linearly search, so it will take 2 to the power n number of times. What about the parallel computer? So we have shown that parallel computer can do much faster than classical computer. So let me make it very clear. Parallel computer means here the supercomputers that we have right now. All right, the powerful supercomputers. So for to search a 2 to the power n info, so to search element, so to search an element from a 2 to the power n search space, we require almost 2 to the power n number of resources to get the output in 1 unit time. Let's forget about 2 to the power n number of resources. Just think about like n number in like 1,000 or 10,000 number of resources. It is very much difficult to prepare a supercomputer with 100 computers, because it will take some space, it will take some resources, it will not cost efficient, it must be cost inefficient, and it will and it is not at all feasible. So what is the alternative? So we have already showed the alternative here. So as I mentioned, that if we have 4 number of formations, then 4 informations, then we can represent them with the two qubits. So if we have 2 to the power n number of information, we need only n qubits. So suppose 2 to the power 100 information you need only 100 qubits to perform that operation in quantum computer. So this is fascinating. Now this is the thing is going to change the world. But remember, you cannot have the desired result in a one shot. You have to iterate your quantum algorithm root over of 2 to the power n times. So you can ask me that, sir, this is nothing but quadratic speedup, isn't it? I mean, classical computers was solving this problem with 2 to the power n times, and quantum computer is solving with a square root of 2 to the power n times. But trust me, this square root can give any organization $1 billion or trillion USD dollars, and it's a fact. And I'll go into that part just a couple of minutes. So I think now it is very much clear that qubits are the main fundamental bits, quantum bits that are required to perform any algorithm, any quantum algorithm. But you have to remember that you need superposition and the entanglement part also to perform the quantum algorithm in the quantum computer. So now I'll revisit the superposition and entangle part again to give the clear idea of what is superposition and entanglement. So superposition, we all know now that we can have a quantum state with all the information at one shot. So that is the superposition. But the main problem is superposition with the main problem with the superposition is that if we observe that quantum state, it becomes classical. It is nothing but the equal superposition of all the states. That means if you observe that quantum state, it will become a classical state, and nothing much than the classical information. So what actually will make quantum computer different from the classical computer, and that is the entanglement. So these are the qubits are can be superposed. That means at a time we can have all possible information in our hand, and the qubits can hold a correlation between them. So that's why they remain what we want to achieve actually. So superposition with entanglement in the qubit part will make quantum computer so different from the classical computer. If you have any doubt or any you need any clarification regarding these properties, you can anytime mail me. So I'll give my mail ID. So if any doubt you have. So now we all know that qubits are the fundamental part of quantum computers. So qubits are required to perform any operation for quantum quantum algorithm for a specific problem. But we need superposition as well as the entanglement part also to perform a simulation or the implementation of an quantum algorithm. So, but quantum computer, or that classical computer also doesn't understand the properties. It understands the gates. Like classical computers have OR gates, AND gates, NAND gates, NOR gates, all the universal gates from which it can understand that what is I'm going to do. And similarly, quantum algorithms quantum computer has their own quantum computer has its own quantum gates, and the most important gates are Hadamard gate, NOT gate, CNOT gate that I have shown in this slide. So don't give too much pressure to understand these gates right now. So these are the fundamental gates, and these are unitary gates that are imposed into the qubits. So these are the qubits we have that's having some 0 0 1 0 1 quantum states, and we impose in such a way. So we impose these gates in such a way that the algorithm can give me the desired result using the quantum computer. So I think we started from quantum computer is a myth. So now we can see that, or we can exhibit that with the help of qubits, with the help of quantum mechanical properties like superposition and entanglement, and with the help of quantum gates, we can implement any such quantum algorithm in the quantum computer. And that is the beauty of it, because back in 2016 it was completely unbelievable. All right, so after that it becomes very much fascinating that anyone can program quantum computing. So this is the last slide from my quantum computing part. So everyone comes with challenges. So present challenge with the quantum computer quantum computer is that it is not having the thousands or hundreds of thousands or lakhs of qubits. It's only having like 50 or 60 odd qubits. And why is it so? Because we are talking about quantum. We are not talking about living people like us. We are talking about quantum. What is quantum all about? It is basically the quantum particles like atoms or the electrons or the protons. So that electrons can have this quantum mechanical properties like superposition and entanglement, but we don't have. So, but we are living much up in the world where the temperature is like 40 degree, 50 degree, or 35 degree, and we still survive. But this is not true for the qubits. Qubits are much smaller. It's a quantum particle. So this qubits needs to have in the absolute temperature, that means to minus 273 degrees centigrade temperature it requires to be in the perfect state. So why it is required in the perfect state? As I told you that whenever we measure the quantum state, it becomes classical. So when it is not in that scenario of absolute temperature, so it becomes classical. So there is no use of qubits anymore if this is not in the environment of such colder space. So you can see that it is a IBM quantum computer. And if you want to understand why it is so big, if you are talking about quantum computer, it must be smaller, and trust me, it is smaller. It is just a small chip fixed in somewhere into this machine. And apart from that small chip, everything which is visible to us is a fridge, is a refrigerator. It's just freezing the environment for being into the state, being in the perfect state of qubits. So what you are seeing here, it is a refrigerator. So we need powerful refrigerator. We have to control the qubits in such a way. We have to control the qubits in such a way that it doesn't become a classical state. So that's why the present challenge is we can have only the 72 or 50 odd qubits machine. So physicists are working day and night, and they are trying their best to have the 1,000 or the billion or the million number of qubits machine in our hand. After that, we can solve the Shor's algorithm or the Grover's algorithm much more faster in down the line 10 to 15 years. But before that, we have this small computer, so we can program it, we can play with it, we can have the knowledge, because when we all need to understand quantum computing that time. So it's better to understand 10 to 15 years back, because after 10 to 15 years later, it will become more difficult. So this is the challenges right now. We only have 72 qubit quantum machine. So from this part, we have a clear visualization of what is quantum computing, what's all about quantum computer. Now our next part is all about the industry prospects in quantum computer. As I am currently working in a R&D company, so I can give you a clear picture where this quantum computing can be useful. What are the field what are the field there in the industry. So this is a slide why investing in quantum computing now, because last from 2012 to 2021, it's all about AI, machine learning, isn't it? So AI almost changed the world, changed our perspective, that we can predict the weather, we can predict, we can have the COVID-19 drug in 1 or 12 or 13 months. So AI slowly changed our perspective, but it creates some gap also. Like for a larger search space, I have already told you that today's most powerful supercomputer fails to simulate or implement that problem measurably. But we have to address those problems also, because as we know that our weather prediction is still vulnerable, it's not perfect yet. So to make it perfect, we need some computer which simulate the historical result in such a way that we can have the perfect weather prediction. We can have the perfect molecular design from which we can design the drugs or so. So that's why it is the best time to invest in quantum computing. And I always tell all the universities and all the colleges where I'm being invited, that you should start a course in quantum computing right now, because we are already late. European or the US or Canada or China, they already started all the curriculum, but we are not very much uh, knowledgeable about it. So we need to start courses in quantum computing. So these are the main sectors, I would say, that quantum computing will have some valuable applications, like manufacturing, private sector, financial sector, telecom sector, resource sector, health sector, almost all the sectors, isn't it? So if you know any sector out of this, I think all the sector belongs to these six sectors. So these are the famous problems, like logistics. You all know that Amazon supply chain logistics, Amazon is all about, Flipkart is all about. So everyone needs a powerful computer to simulate their algorithms, so that how they can efficiently take the orders and supply the order into the owner. So these are the problems, these are the classical computer science problems that we are dealing right now. And if quantum computer comes into the action, these problems will be addressed more significantly. In public sector, so you can see that yes, crypto analysis, I have already told you that yes, it will break RSA crypto system. Like in financial services, you can be rich. I'm not joking. You can predict the stocks with the historical data, and you'll be rich. So in telecom sector, you can see that post quantum cryptography, yes, yeah, uh, it's a um, it's a term you should know about it, because when quantum computer will come, it will break the RSA crypto system. Then what's next? So we need some post quantum cryptography that will hold this system in such a way that no quantum computer will break that system. Okay, because we don't want to lose any money from our bank or the Facebook's password. All right, so next is some all right, Shonali ma'am, I need another 5 to 10 minutes. Is it okay? I mean, it's almost 1 hour. Is it okay that if I
Yes,
take?
yes, you can take.
Yeah. Thank you. So so I have seen that there are two more sectors. One is resources and services, where like oil. So where smart grids, how the smart grids uh, can be implemented, that can be optimized through quantum computers, and so. And in health sector, yes, this is the sector I must talk about, because this sector, if quantum computer comes within 10 years, this sector will be changed, because as we all know that uh, to discover a drug a COVID-19, we need to understand the protein structure of the virus. So if we have the powerful computer, quantum computer, then it will be easy to understand the protein structure of that particular variant of virus, and it will be much faster to prepare a drug for it, isn't it? But I warn you that it won't be possible in blink of an eye. It will take time, because all the problems are NP complete problems. We are not talking about the polynomial problems, and we saw that NP problems are exponential. So if we have some NP intermediate problems, that could be possible runtime in polynomial time, as I mentioned, Shor's algorithm, that is NP intermediate problem. But for like we all are excited about the NP complete problems, because those are the problems which are having the most of the real life applications. So those problems cannot be implemented quadratically faster, cannot be implemented faster than quadratic time. What does it mean? So I show that it takes square root of time, that is known as quadratic speed up. So we don't have any polynomial time reduction such incident or such algorithm till today, that can perform that can solve any NP complete problem in polynomial time. It only solves in a quadratic time of 2 to the power n. But I already mentioned that will give an organization maybe billion or trillion dollars. So I just described more elaborately in these slides, the chemistry sector will be benefited with the quantum computer when it will come. And you can see that just for a single spark, I want to share a variational I want to share a term, that variational quantum algorithm that is been used to solve chemistry problems. Pharmaceuticals, already I have told that it will change pharma field with its pattern matching ability or the by solving the NP complete complex problems. Cryptography, I have mentioned several times, so I'm not going to tell much. Finance sector, I have already covered this also. So it will predict the so when quantum computer will come, it will predict the stock, and you can become rich. So most powerful quantum computer. So those who have most powerful quantum computer will be richer very soon. Oil prospection is another sector where because we know we live in India, oil is now reaching 100 or so. So if we optimize the oil prospection in such a way that that from that area oil can be found, good oil can be found. So it may be becomes it may be decrease little bit. I hope so. Next is the famous combinatorial optimization problems, like traveling salesman problems that is been used in Amazon, Flipkart, and all the logistic and the logistic companies. So this is famous problems to our computer science students also. This problem can be solved with much faster time, and using like just learn this term QAOA, or the quantum approximate optimization algorithm, is currently being used to solve these combinatorial optimization problems. It can be also useful for machine learning, as machine learning requires lots of data. So you have to you have to fetch those data into the quantum machine, and you will have the advantage of it. So this is the so from this column, you from this row you can see that this is the numbers of billions that China has invested, United States has invested, or India is no longer remain backseat. India has also invested 1.27 billion USD, which is near about 8,000 crore in 2019 or in 2020 for 5 years, and Europe also invested like 1.2 or 1.1 billion USD. So these are the main companies other than us. Atos, IBM, Google, Microsoft, Intel, Honeywell, they are making the quantum computers, scalable quantum computers. So you can see that NISQ era is going on. That is noisy quantum computers. We hope that maybe not 20 years, it should be corrected. I hope that it could be possible that down the line 10 to 15 years we'll have this scalable quantum computers. So some startups, well-known startups like DOF, Rigetti, Silicon Quantum Computing, Cambridge Quantum Computing also came up with their ideas of establishing the quantum computers. So you can see that that the organization are coming up in I mean, most of the organization are interested working with quantum computing right now. I haven't mentioned here, but in India, not only Atos, Amazon, Infosys, TCS, HCL, all the and many more startups are also interested to recruit employees to work on quantum computing. So there is a bright future in for the students who have already started learning quantum computing. They must have a bright future. So as I'm representing my company Atos, so I'll take just 2 minutes here and I'll finish it off. So as I'm representing my company Atos here, so we mainly I already told you that we have a most powerful quantum simulator right now, and this comes up with a quantum
Recording stopped.
Quantum programming platform. So apart from quantum programming platform, we also provide quantum expert consulting services that in this project I'm working, and we are also believe that we can provide new generation architectures of quantum powered accelerators in the supercomputers, and we are also researching on various quantum algorithms and the quantum safe cryptographies. So this is specifically for the students who are listening patiently for my presentation. There are the 5 takeaways we can take from today's discussion. First one is quantum computing is not no longer a myth. It's a well established domain to work on. Second is there are 2 important quantum mechanical properties, which are superposition and entanglement, which makes quantum computing different and powerful from the classical point of view. And I have already discussed the present challenges that we have, like number of qubits are very much limited, so quantum computers are more error prone, and we cannot implement very complex or large problems into today's quantum computer. Industry prospects, I elaborately discussed about it, and the last and the important part is what can you do with quantum computing today especially for the students. So you can program quantum computer and take a look at the available tutorials, courses, videos. So I just gave a 1 hour lecture, and for a subject or domain like quantum computing, it's not enough at all. So you have to look for much more valuable tutorials, courses, videos to understand the philosophy of quantum computing. And if you know any of the languages like C, Python, anything, so you can start programming yourself in the quantum computer. And to get all the job related information, you should have a LinkedIn and ResearchGate profile. From these social network sites, you can get all the job related description regarding quantum computer. So that's all from my end. If anyone have any questions, I'd be very happy to give answer.
Amit, I have sent you some question in your chat.
Okay, thank you, Chilambi. Chat, okay, chat, yes. Well, so is it, so these questions are from one person or the several? So these are individual questions.
From several person.
Okay, so
individual questions.
Yeah, these are individual questions. Okay, all right. So what is Qiskit? So Qiskit is nothing but it's a platform. It's a quantum programming platform or the quantum simulator that is offering 32 qubits quantum simulator by the IBM. So it is completely freely available. You can access Qiskit by installing the Python platform. All right, so you can program on Qiskit for the specific problem. What is the difference between quantum computing and artificial intelligence? Artificial intelligence is it's more about algorithmic perspective. I mean, if you have a problem, like if you have a computational problem, so artificial intelligence is a tool or is a technique, or it gives several techniques to solve that particular problem in such a way that the accuracy of the results or the accuracy of the desired result can be gettable. All right, but quantum computing is all about quantum algorithms. It has separate number of algorithms that can solve many or all computational problems. But we are not bothered about the polynomial time problem, because classical computer or the supercomputer are enough to solve polynomial time problems. So we are more concerned about the complex NP problems that can be solved the quantum computing or the quantum computers. Which one is better, artificial no, don't take it in this way. Artificial intelligence is more about a classical thing. Quantum computing is a different paradigm. So I have already answered the previous question. I think you have understood the your answer of the question as well. What are the merits and demerits of application? So it's not completely understandable to me. What are the merits and demerits of the applications? Like applications, so I'll try to answer this in this way. Like application is nothing but like you are using some Android or Android phone. Okay, so there are several applications you can find from Google Store, and applications just help you to understand the world in a bit better way. So we are not here to talking about the merit or demerit of the application. Like PUBG is also an application. It has many demerits. You may agree disagree with me, but it has some demerits. But we are here to talk about more complex system, not the applications. System, we have to build such a system that the applications, that the complex application could be run in future. All right. So how can be quantum circuits be designed? Good question. So it's a first of all, it's a problem specific. You have to understand the computational problem first, which problem you are targeting. Like you have to fetch, like anything we do, we can fetch that that work or that thing into a computational problem. That computational problem we have to understand, and from that computational problem we have to understand which tool or which technique or which algorithm will solve that computational problem. After getting the information of the algorithm, then we have to design the quantum circuit for that algorithm and for that specific problem. So quantum circuits are completely problem specific. Please tell which are the quantum computers in India. This is really tricky. As far as I know, we are still researching. All right, we Atos only provides quantum simulators. It likes so we provided quantum, most powerful quantum simulators to Indian government. So right now we are more focused in quantum simulators, but some labs, like I know TIFR from Mumbai, or it's maybe NIT, I may be wrong, NIT from Kerala, or IISc from Bangalore, or Raman Research from Bangalore. They are working on the quantum computers. But as far as I know, it's maybe 5 qubits or so we have right now in India. But if you are talking about our organization, we are solely working on quantum simulators right now to train the upcoming researchers to all and the organizations that whenever a quantum computer will come, they will get all the benefits. Can traditional transistor will achieve quantum property like superposition, not entanglement? Great question. It's a complete no, because traditional transistor can hold 0 or 1, isn't it? So it holds only the classical bits. But to hold quantum states, you need qubits, and to hold that to prepare that qubits, you need different technologies. 5-6 technologies are there which are really in the race. These are like superconducting or superconductors, ion trap, quantum dots, linear photonics, non-linear photonics. I almost covered all, I believe. Or topological quantum computer Microsoft is doing. So it's a very good question. Please share research areas in this domain. So I just told you in last 10 or 12 slides that what are the research areas or the research domains or the research sectors for the quantum computer. I think you have understood it very well from the slides. Or if you have any other question, or if you haven't understand properly what I have told today, you can reach me through mail. I think that's all, Jilamdi, from questions.
These are all questions from audience.
Okay, that's great.
Okay, thank you, Amit sir. This is a wonderful presentation. So many participants had asked for the presentation. I don't know how much you can give, at least for the application part. You can suggest our students who can apply in their future scope. And thanks a lot for coming. Now I will request our HOD sir to felicitate you Sir, 1 second. Amit sir, you need to stop your screen
Yes,
sharing, I think.
yes.
Have you stopped it?
Just a minute. Yes, yeah, I have already stopped it.
Okay. Sir, HOD sir, can you hear me? DPS
Yes, madam.
sir?
Yes,
Okay,
madam.
okay,
Yes,
sir.
madam.
Yes, sir. Sir, is it coming?
Yeah.
Yes, sir. So, Mr. On the behalf of the CSE department, yes, College of Engineering, this is the small token of appreciation from our side. So kindly accept it and
Thank
do
you
the
so
honor
much.
to us.
Thank you so very much.
Thank you, sir. Thanks a
Yes,
lot.
madam, it is very
And I would again request our HOD sir to give the vote of thanks for today's webinar. Sir.
Thank you so much, madam. Yeah, thank you, madam. So first of all, I can say that the good evening to all the participants and good evening to the speaker. So I would like to thank our principal sir first because sir has given the idea we can go for the webinar on some cutting edge technology which is required in the future. I would also like to thank the our registrar Madam Sheila Singh Ghosh, and I would also like to thank the today coordinator Sonali Madam. Madam, due to several problems after she has managed the one webinar there, so it is a very good feeling. And the topic for the today webinar is very wonderful. Quantum computing part is there. I would also like to thank all the participants because without the audience, program is not successful. So I can see that through the YouTube live, many audience have joined, and I hope that they are enlightened by the knowledge of the quantum computing shared by the today's speaker. And I hope that it will be create the one seed within the all the participants so they can cultivate it, and in the future they can go for the research in quantum computing there. So last but not least, I would like to thanks to the today speaker Amit sir because sir we have covered all the part of the quantum computing. Thanks for the your wonderful and mesmerizing session there. I can see that question from the audience. They are asking that. So it is a very good thing. And quantum computing, as I already mentioned, is the future of computing there. So we expect that more lecture from your side and
Definitely.
great bonding with the Jazz College of Engineering CSE department. And in the future, we hope that we can give the lecture to our students, those who are interested in this area. So this is the just the beginning of the good relation between you and our department, and it will be continue in the future, sir.
Yeah,
So thanks
definitely.
to the also our lab staff there because
Yes,
when
sir.
we can plan any webinar, so we know that we require the help from all the side, small help, but it required the help from the all the side there. So thanks to all the participants. If I miss anyone, so forgive. Just give me the excuse me, but it is a good because we can see that the good technology will be required in the future because sir already mentioned that some problem of the cryptographic that when the quantum computing will become, it is very easy to crack the algorithm which is nowadays not possible to crack it. So we can think in the future, and in India we can also implement this type of research because I already mentioned in China it is already going on. So it is a very good thing, and I hope that our participant will be listen it and they can go for the research there. So thank you to the all the participants, and also one more time I would like to thank our coordinator of today program, Sonali Madam, for organizing this type of wonderful webinar there. So Madam, thank you to everyone, and Sonali Madam, over to you.
Okay, sir. With all others' permission, can we close the session?
Yes.
Sir, madam, will
Yes.
anyone will talk to our
Yes.
resource person?
Yes. If anyone has any question, I'd be very
Yes.
happy.
it was a resourceful talk and so insightful.
No, actually,
presentation.
I tried to make it more
You
simple.
see,
Yeah.
I
Because
repeatedly
without mathematics, it is very difficult to describe
Yes,
quantum computing. So
I
I
repeatedly
tried
asked
to
to make it simple
yes. That's why
for
I
our students, and
yes.
the topic is so vast and so. Okay, so with all your permission,
Yes.
we are concluding here.
Okay.
So
Thank you
okay,
for
you all,
inviting me.
and
Yes.
good night.
Right. Good
Yeah,
night.
thank you everyone.
Thanks. This is our pleasure. And thank
Okay.
you all. We are concluding here. Good night, everyone. Stay safe and healthy. Okay, goodbye.
Bye.